Good evening. Before I introduce tonight's speaker, I want to express on behalf of OPB our appreciation to the supporters of the ICEP lectures, both the corporate and institutional sponsors and all of you individual subscribers to this excellent series. It has become a significant part of the cultural and intellectual life of our community, and we're looking forward to the 1992-93 series that starts this October. I also want to call your attention to the information on the back of tonight's program. It's about an upcoming broadcast on OPB television on May the 13th. A 90-minute block of family viewing starts at 8 o'clock in the evening, and it includes What Kids Want to Know About Sex and Growing Up, followed by A Conversation with Magic, featuring Magic Johnson speaking with children about AIDS. Both of these programs are outstanding. Please be sure to watch and urge your family, friends, and colleagues to do the same. And now, about tonight's distinguished speaker. Dr. Lynn Margulis has made the most substantive contribution to evolutionary theory since Darwin. She pioneered fundamental insights about the central role of cooperative relationships in evolution. Margulis argues the mechanistic worldview has many problems, one of which is the failure of neo-Darwinian biologists to think physiologically and to recognize the principles of self-organization. Lynn Margulis is a distinguished university professor in the Department of Botany at the University of Massachusetts, Amherst, a post she has held since 1988. She earned her undergraduate degree from the University of Chicago, her master's degree from the University of Wisconsin, and her doctorate from the University of California at Berkeley. Professor Margulis held a Sherman Fairchild Fellowship at the California Institute of Technology in 1977 and a Guggenheim Fellowship in 1979. In 1983, Dr. Margulis was elected a member of the U.S. National Academy of Sciences. Her work influences science students of all ages. She has developed teaching materials for science classes in elementary schools and on up through the graduate level. Her publications span a wide range of scientific topics, including groundbreaking work in the areas of cell biology and microbial evolution. Margulis has helped us understand that new symbiotic partnerships, even between species that may once have been enemies, is fundamental to the next phase of the evolution and expansion of life in the universe. Her writing has been described by the New York Times Book Review as clear, evocative, lyrical, and lucid. Not merely painless, but positively thrilling. I would add insightful and provocative to that list of adjectives. So, without further delay, ladies and gentlemen, please give a warm Portland welcome to Dr. Lynn Margulis.
Thank you. Thank you very much. I hope you can hear me well. Thank you very much, Ellen Block and Terry Bristol, and especially the Portland Public Schools. That introduction was impossible to live up to. I don't think that I'm comparable to Darwin, and I don't think that you're going to leave thinking that I am at all. But I appreciate, with all humility, I appreciate that. And then if you can take those lights, these lights off my eyes, Jens, I would be very grateful. That's right. Thank you very much. Much better. I want to talk to you today about this Gaia Hypothesis, which you can think about as kind of a recombination between the lively imagination of the atmospheric chemist, Dr. James Lovelock, and the space program, that is the International Space Program. And the idea is we're going to explore this hypothesis and try to state it in various ways. It's really difficult to give an exact description that everybody can agree on, but I think that by the end of the hour or 45 minutes, you'll have a good idea of what the statement says. And I will claim that it's entirely in the context not only of science, but of evolutionary science. It's definitely consistent with general evolutionary views, but it's far broader than most scientists who call themselves evolutionary scientists or evolutionary biologists. So we'll get to the idea of what is the Gaia notion. And as we do that, we will take some sideway glances at live material, organisms that are very related to the Gaia phenomenon. And the Gaia phenomenon roughly is the concept that what we've been considering to be the environment, out there as the environment, is really part of the system. That we are embedded in a single system of life that is both continuous through time and through space, and that life has modified its local environment. And it's modified the local environment with respect to the temperature at the surface of the planet, the acidity and alkalinity, and the interaction of the reactive gases. That's one way of stating it. The simplest way to think about it is that we're wrong when we consider the environment as separate from the system. The environment co-evolves with life, and in fact the environment of life at the surface of the earth is space. And what we tend to think about the environment is really part of the living system. There's another way of saying it. So if I can have the first slide, or I just push the first slide here. I think the slide projector has to be put on back there. Just turned on, and then we'll be all fine. I'm pressing, and nothing is being forwarded. The light needs to be put on. Just the switch has to be pushed forward. High tech. And we'll get the lights halfway down. That's just push. It worked 2 minutes ago. I'm sure it's going to work. Just push the lights on. Okay. So throughout this talk, we'll be having various ideas of what this means. And I'm sure you all recognize Gaia as the ancient Greek goddess of the earth. It's the same word that you're all familiar with when you use the word like on. I haven't done anything. Back. We'll work it. Somebody fell off. No, it's sitting there.
You have to use the podium mic.
Oh, I can't stand the podium.
Let me see if I can get the
back door version of this.
Give me that, and I'll see.
Okay. Well, this is all high tech, right? Here. I really got to get it fixed, though. It's probably the switch. Okay. The word geology, geography, Pangea is simply another pronunciation of the same general word for earth. Geography, writing about the earth, geometry, the measure of the earth. And that all comes from Gaia, an ancient word for the earth. And as we can see, as we will see, it is a concept where what we have been considering the environment is really part of the system, and I will try to explain what we mean. Now, here's a picture of Lovelock, who comes from the Devon-Cornwall border in the southwest part of the United Kingdom, and here is one of his garden statues of Gaia. And you see him actually in his native environment. He works on gases of the atmosphere and has made quite a reputation in several other fields of science. He developed the electron capture device for the gas chromatograph and various pressure devices, and he's a fine inventor. And it was in the course of measuring the gases of the lower atmosphere that as a chemist he recognized that the gases make no sense, and we now have got a listing called the Gaia Hypothesis comes of age because we now have 21 publications, 21 years of publication about this hypothesis. Somewhere halfway through this, perhaps in the early 70s, Lovelock, in great frustration, told William Golding, the author of the novel The Lord of the Flies, that he needed a good four-letter word to focus the attention of his scientific colleagues. And Golding immediately came up with the word Gaia. Prior to that, he had written many papers on the hypothesis, but because it had no name, people couldn't understand it. And now that it has a name, people have something to attack. Now, one of the most notable pieces of background information about the hypothesis is that astronomers tell us that through the course of its history, the sun has become more and more luminous. That is, the sun has heated up. And, of course, the Earth and the planets on either side of the Earth should simply have correspondingly heated up over their history because the major source of heat for the Earth is the sun. On the other hand, we have evidence that the Earth's temperature has stayed constant or decreased. We've always had liquid water. Water was not frozen, nor did it ever reach boiling. This anomaly, the fact that the Earth's temperature seems to be staying constant in the face of perturbation, was one of the aspects that led Lovelock to state the hypothesis. So when we say that the Earth's environment is maintained by life, one aspect of that maintenance is the maintenance of constant temperature, or roughly constant temperature, that the environment has stayed remarkably, the temperature of the lower atmosphere has been remarkably constant, and it may come as quite a shock to you to realize that the mean mid-latitude surface temperature of the Earth is about 17 degrees centigrade, in other words, room temperature. And the Gaia hypothesis says that's not by chance alone, it's because of active regulation, active homeostasis, active geophysiology. The Earth is a physiological being by this reckoning. Now, another big aspect of the hypothesis is the comparison of the Earth to the two planets on either side. Here we have a picture of the very cloudy second planet in the planet Venus, to which probes have been sent over and over again, most of which we don't know about because they were sent by the Soviets. You can see, for example, this is a view of the surface of the planet Venus from Venera that was sent in October of 75, and it landed in January of 76, and you can see what foreign power or extinct foreign power it belongs to. But at any rate, the Russians have put a lot of soft landers on Venus. Here's another picture of the surface of Venus from the spacecraft. And one can say that with equanimity that Venus is very hot, it's extremely dry, and it's basically a carbon dioxide world. It is extremely unlike the Earth. It's a sulfur-rich carbon dioxide world. Now, if we go to the other side of the Earth, in other words, to the fourth planet in the solar system, Mars, as many of you know, the United States launched the Viking spacecraft in 1975. Here's a picture of Mars from orbit. As we close in on it, the Viking spacecraft left, two spacecraft actually left in 1975, and they landed on the planet in 1976. And again, ground-based astronomical observations were confirmed. Mars, although its atmosphere is much thinner, is a very cold, a very dry, a completely lifeless planet. And even these things which look like rocks, often they fell apart when they were lifted up. They're not even consolidated rocks. Mars and Venus are extremely unlike the Earth with respect to certain properties. They certainly are not room temperature. Some people call it the Goldilocks problem. Venus is too hot, Mars is too cold, but the Earth is just right. Now, both these planets are carbon dioxide dry planets. And we know that the early history of the entire inner solar system was quite comparable. Here we have a photograph of the Viking, from the Viking orbiter of the Martian surface. We see these features that people attribute to water. That is, these are rivers that were present early in the history of Mars. And after the rivers, there were impacts due to meteorites. These are meteoritic crater impact features, and it has been said that the last time it rained on Mars was over 2,600 million years ago. It's really dry. It's been dry ever since. So if you think you have a drought. And one of the interesting things is that Mercury, Venus, now Venus with the new Magellan, and Mars and the Moon have all shown direct evidence of the early meteoritic impact craters, of the cratering of the early solar system. Now, if we do the same approach from the Apollo spacecraft of the Earth, we're struck by certain things. First of all, the absence of carbon dioxide, the moderate temperature, the overabundance of water. The Earth is really a weird planet. We can drop the Viking camera. This picture was taken with the same camera made in Tewksbury, Massachusetts, the same camera that took pictures of Mars that we just saw a minute ago. And the picture was taken in the Colorado desert to show people at NASA and elsewhere that clearly there's no life on Earth. Now, the response of one NASA official was that, no, there's just no life at Martin Marietta, where the picture was taken, which is a little unfair statement. But the basic idea is that with the camera alone, there's no real way of telling whether or not a planet has life. And when confronted with this kind of evidence, Lovelock realized that the camera will never tell you about the presence of life. What you really need is a good gas analysis, because with a good atmospheric gas analysis, you can tell immediately that the planet, whether or not a planet has life. And his logic was that living organisms always and constantly exchange gas with the atmospheric and fluid surroundings. It's not just your roommate and your spouse. Everyone is exchanging gas all the time with the atmosphere. And that gas cannot hide. It must be detected. And his gas analysis told him that the Earth is bizarre. It has no carbon dioxide virtually. It has a violently reactive gas, oxygen. It is really not understandable from a planetary or chemical point of view without recognizing the presence of life. Now, here's another picture with the same sort of camera, and we see that the Earth, just like Mars and Venus, has evidence for volcanic features, volcanic and meteoritic impact features. The early solar system was the same on all of these planets. Here is a picture of the Moon from one of the Apollo orbiters, and here we have a photograph of a close-up of a meteoritic impact crater on the Moon, and we can say that the Earth was cratered, the Moon was cratered, Mercury was cratered, Venus was cratered, and Mars were cratered. They were all subject to meteoritic impact cratering early in the history, very early in the history especially. There is still some cratering going on, but it's much less frequent. To give you an idea of the size and the impact of these craters, this is an actual photograph of a crater in which, to scale, has been superimposed not the state of Oregon, the state of Rhode Island. Now, I admit that Rhode Island is somewhat smaller than Oregon, but it gives you a very clear idea that craters on these bodies, inner bodies of the solar system, were as large as the entire state. In other words, there was a huge amount of very serious cratering early in the history. And we have rocks. This is a photograph of a close-up of a rock that's made of these little particles, a very old rock from the Earth. And the name of this mineral, or this mineral matrix really, is impactite. In other words, it's a rock made by little particles from meteoritic impact craters on the Earth. So we know that the Earth was subject to the same sorts of conditions that Mars and...
Do you want to give it one more try?
We'll try it, yeah. And here's your picture. We're going to... Yeah. Good. Sounds like we've got this microphone working. Is that good? Yeah, okay. And here's a picture, a Smithsonian artist's rendition of the early inner planets. And this could be any of the planets. We have volcanic activity, lava. We have meteoritic impact as evidenced by these rings. And this is a pretty good idea of what all of these planets were during the Archean eon, that is between roughly 3,500 or 3,900 million years ago. And there's no reason to believe that these processes hit the moon and didn't hit the Earth. Of course they hit the Earth as well. This is a typical planet. We all started the same. Then to what do we attribute the very big differences between the Earth and these other planets if we all did start the same? Water, we have direct evidence, was on all of these planets from the beginning. So here is an artist's picture of what early planets would be in the absence of life. You have volcanoes, you have impact craters, and with time, hydrogen goes off, CO2 stays because of gravity. You have mostly a CO2 atmosphere with trace amounts of nitrogen, trace amounts of oxygen, trace amounts of water. And this is really what the planets should look like, all of the inner planets that can retain an atmosphere. But indeed, this is what the Earth's atmosphere looks like. There are volatile particles a meter across that tend to go sideways. There are gases like butyl mercaptan, which I don't know how frequent it is around here, but in the countryside around Amherst, Massachusetts, it's one of the most conspicuous gases. You recognize that, of course, as skunk odor. You have gases like methane, which you burn in your stove, that are utterly chemically incompatible with oxygen. You have epoxide compounds that are violently reactive with oxygen. You have a mixture of particles and gases that are entirely inexplicable by chemistry alone. It was the consistent measuring of things like camphor and eugenol and myoporum that led Lovelock to recognize that the Earth, in a qualitative way, is very different from a planet determined by chemistry and physics alone, and it led him to the idea that it is life at the surface of the planet that is making the vast differences between these various bodies of the solar system. And you can see this when you graph that. You can see the basic concept. Mars' atmosphere, these are the atmospheres of the planets, the three planets compared. Mars's atmosphere is 95% carbon dioxide, virtually no oxygen, that is trace amounts of oxygen and water, and something like 2 to 3% nitrogen. Venus's atmosphere is something like 95% carbon dioxide and 2 to 3% nitrogen. The Earth's atmosphere is completely different. It's almost 80% nitrogen, and it's got over 20% of this violently reactive gas, oxygen, and there's evidence that oxygen has been around for a very long time. On a planetary scale, the Earth is very different from its neighbors. It shouldn't be different from its neighbors. Now, what's wrong with the Earth? The Gaia hypothesis states that these chemical anomalies are produced by life and retained by life because the Earth is essentially a physiological being, whereas these two are dead planets. The Earth's planetary composition is one of a reactive mixture with potential to do work, whereas Mars and Venus are spent and dead. What are the big differences? Well, one of the major ones is the absence of carbon dioxide and the presence of oxygen. Now, here's one way of stating the Gaia hypothesis. As I say, there are many ways. But the hypothesis says that the biota, which means the sum of the live organisms, that would mean the fauna, the animals, the the flora, the plants, and the microbiota, the sum of the microorganisms, that the biota is embedded in the biosphere. The biosphere is the place where life exists. It goes from about 12 miles into the abyss of the ocean up to maybe 8 miles to the top of the troposphere, that top of that part of the atmosphere. It's a little ring, maybe 20 kilometers over the surface of the Earth. The biota embedded in the biosphere. Over 30 million types or species or kinds of organisms, of live beings, all of which are descendant from common ancestors, in fact, common bacterial ancestors, all members of the 5 kingdoms, which we might talk about later, but the plants, animals, protoctus, fungi, and bacteria. That is, all of these 30 million organisms produce and remove gases. They produce and remove organic compounds, metals, and other ions. The interactions of these organisms, their growth and metabolism, and their interactions, behavioral, metabolic, and genetic, the sum of their interactions, especially in a watery solution, lead to the modulation of the Earth's temperature, a retention of the Earth's temperature